Well, it's my pleasure to welcome Adam Beardsley to this MWA meeting that we've been having this week. So Adam is principal scientist for the MWA, which you will find out is a very difficult job because the project covers a lot of different science cases. And so, but Adam has kindly offered to provide an overview of science with the MWA, where it's been and where it's going. Thanks all for coming. Hello, everyone. So, as Jonathan just mentioned, I'm representing the MWA here right now, but almost everything that you're going to see today is actually not really my work directly. I work with a lot of people, and almost every plot that you're going to see is coming from many other people. And in fact, a lot of them are across the hall in a meeting that we're having right here at Brown this week. And this is a photo we took this morning. It represents a lot of different people. Folks from around the world are here to share ideas, work together. So, I thought I would I'll go back to my title here. So, the talk is going to be kind of structured as a summary of science that we've been doing with the Murchison Widefield array. And I'm going to try to, when I can, distinguish between the two phases, phase 1 and phase 2. I'll talk about what those two mean, but essentially they're almost two different arrays because we've had a lot of upgrades over the years. So before I go into upgrades, maybe I should tell you what the MWA actually is. So it's a low frequency, we're talking 80 to 300 megahertz, so that frequency range. It's a wide field of view, roughly 30 degrees in field of view. It has a high sensitivity, and it's a very versatile radio telescope. These, I guess versatile might be a little bit redundant here because a lot of these kind of factors play into that. You have a very high sensitivity wide field telescope. A lot of people are going to want to do a lot of things with it. And in fact, early on, the MWA was structured with kind of 4 primary science themes. The epoch of reactivation, galactic and extragalactic science, time domain astrophysics, and solar, heliospheric, and ionospheric science. And actually, so this slide is going to serve as the outline for my talk. I'll kind of cover more on the MWA itself from an instrument standpoint, and then I'll start diving into the different science themes that we have with the telescope. So the MWA collaboration, though, is made up of, last I counted, which it fluctuates, but it's 268 members, spread across 6 different countries, plus there are associate members that are in a few other countries, such as the UK and India. But these 6 countries are the partner nations. And kind of highlighted are the actual countries. So, US, Canada, Australia, New Zealand, China, and Japan. So, just kind of come back to the same photo again to show you the MWA. I understand that most people here are physicists, so may not be as super familiar with the radio telescope and what that means. It might look a bit different than a telescope that you're used to seeing where you look through something, or even the ones that have the big dishes. The MWA is made up of these kind of dipole antennas. They're gravity-or antennas, essentially, with some low noise amplifiers. And then there's this little box over here is a beamformer, which is going to beam the signals from that the dipoles are receiving, so you can kind of point the array. So it's non-mechanical, but it's pointing in different directions. There are then 128 of those kind of, we call them tiles, these kind of square apertures out in the desert. It's in the Western Australian outback. So I'll talk about it in a second. See what else do I want to say here. An SKA precursor, so a square kilometer array, built on the site of the SKA low, and it's driven by, it's trying to prove out different technologies and science cases for the SKA. So we've been observing since 2013. We have over 30 petabytes of data. That's actually out of date. A bit higher than that now. So this is definitely kind of big data regime. There's a lot of data you can go through. And then the last thing I'll mention on this slide is this voltage capture, which is going to come in later on. So we are actually able to write down the signals from the antennas directly at very high time cadence. So it's like something like 100 microsecond time cadence. So you can do very fast transient stuff. Okay, so why the Australian outback? This is kind of a fun visualization using this website, radio.garden, which allows you to kind of pan around the world and you can listen to radio stations from all over the world. So you may have noticed the frequency band that we're looking at, that we were tuned into, 80 to 300 megahertz, includes a lot of bands that humans like to communicate with, including FM. So it's a good idea to get away from people as much as possible. And see, like, North America is just splattered with FM radio stations. Europe is just insane. If you compare that with Australia, you can get away from people pretty well. So this is, it's not like completely barren. There are people there. Perth is down here. Should also not have an FM station. Maybe it's just not on this website. It's over here. And the crosshair is kind of right on where the telescope is. So you need a balance between being away from people, but also being accessible. So you have to actually get out there to build the thing and to maintain it. Just another a Google Map view is exactly where it is. So I like to tell a story about how when you go there, you fly across the world to get to Perth, and then you drive, I think it's about 8 hours out into the desert. You reach the end of the road, and then you keep going for about 3.5 hours to reach the actual array. And it's really cool because the road actually ends right at the end of where the turnoff is for the last mine. It's a sort of big mining mission. So that makes a lot of sense. Okay, so we have our setting. We're going to go build this telescope out in that desert. What does it actually look like? This is just a nice drone video. I kind of already talked about the kind of structure of these antennas, so we can kind of, maybe we can't. There we go. We just kind of fly over it a little bit and look at. So these antennas, we're in what's called the core right now. Very dense. A lot of antennas are very closely packed together. We do that to get high sensitivity to large structures. So these antenna kind of separations are measuring the Fourier modes of the sky. You can think about a radio telescope as being like a software lens. You're going to do the kind of inverse Fourier transform that a lens would normally do in optical. You do the software with a radio telescope. So this is, I think, about a third of the tiles are in this what we call the core, and then they expand. They reach out a lot further. This is the phase 1 layout. It gets a lot harder to photograph the thing when you're actually, because there's a high dynamic range between the size of the antennas and the extent of the array. So you can just plot it. It's a little easier to do that. But you can see how it gets out to a radius of about 1.5 kilometers. And this is the phase 1. So we observed with the phase 1 array from 2013 to 2016. And then we incorporated a few upgrades. These didn't happen all at the same time, but the big upgrade is the new antennas, which happened in 2016, and then these other things kind of have happened along the way. So I'll kind of talk about each of these separately a little bit. So the added antennas, so we can correlate, we can observe with 128 antennas at a time, or tiles. I can't remember which one I'm saying. Antennas or tiles, they use those interchangeably. We can observe with 128 at a time. So we have 128 new ones, but we have kind of adopted this 2 configuration setup so that we can observe a compact configuration with the blue antennas. And the inner part of this chart is showing a kind of linear radius, and it's highlighting the kind of regular structure of those two hexagonal additional cores. So now we have actually 3 cores in the array. 2 of them are these kind of regular hexagonals. But then you run into this problem again with the dynamic range of the layout. So outside of 200 meters, it's a logarithmic plot, and so it actually goes out to a radius of about 3 kilometers. So in that extended array, these orange squares, we've improved our angular resolution by about a factor of 2. Another video, because why not? So these hexagonal cores do a couple of different things. The biggest thing is that because they're regularly spaced, and the way a radio telescope works is what you care about is like the measurement between 2 antennas. You're doing a cross correlation between them. And you have a lot of what we call redundant spacing. So many pairs of antennas are actually in the same spacing as each other, so they're measuring the same thing over and over again. That can give you improved sensitivity, and it can allow you to do some other things I'll talk about in just a minute. So that's kind of the aerial view of the compact array. We're not going to do a flyover of the extended array, but it introduced new technical problems because all those tiles in the previous, those antennas in the previous video, are all connected through coax cables and are actually powered over those coax cables. That becomes a challenge to send the signal and the power along that 3 kilometers. So these are actually solar panels powering them, and they have RF over fiber to transmit the signal back to the receivers. With those that extended array, this is kind of a kind of demonstration of the improved resolution. So this is Fornax A, one of the brightest radio sources in the sky. From phase 1, you can make out, if you're familiar with radio galaxies, you have these bright lobes, and you have the nucleus in the center there. In the phase 2, you can just make out a lot more structure in those lobes, and you can pick out a lot more sources around it as well. What's the angular scale? Oh, I clipped that out, didn't I?
When you're 30 arc minutes or so, I want to say.
Sounds about right, yeah. It's a little bit less than a degree across. Okay, so with improved resolution, you can make out fainter sources because they're not contaminated by the point-square function of the brighter ones. And so we expect that the new data is going to be able to probe deeper into the radio sky. Other upgrades that we've kind of taken on are improved or new digital backends, which includes voltage capture buffer, so we can actually keep 150 seconds worth of the antenna data in a buffer, so that if we receive a trigger, we can dump that to a disk and actually have negative latency, which will be pretty cool in some of the science we'll talk about in that. And then the other is Breakthrough Listen. I don't know if you guys have heard about the Breakthrough Listen initiative. Basically money from people to try to figure out if we're the only intelligent being in the universe. So it's a search for extraterrestrial intelligence project. And they've put together a setup where we have a fiber link directly from the telescope to Curtin University in Perth, and they can process the data in real time as it streams in. And this, it opens up the door for a lot of other kind of commensal instruments. We can now attach whatever backend we want to just tap into that data stream.
Sorry, you're saying you have a 1,000-mile fiber that runs back to the university.
Right. 1,000 mile, I don't know.
Sounds good.
Sounds about right.
Well, you said 11 hours then.
Yeah.
So, maybe 1,000 miles.
We'll say that. Whatever that drive is. Yeah, exactly. So, And then the other upgrade is a rapid response system. So we can automatically trigger to receive an alert from the astronomy community. LIGO detects gravitational wave. We can automatically interrupt an observing program, point the array in a direction specified and observe. There is a latency to that because it takes some time to repoint the instrument, and there's a few other technical details to that. I'll describe it in class at all. This is not the limiting factor, though, right now, with things like gravitational wave or LIGO and Virgo are the limiting factors there. And, combine the rapid response with that voltage capture buffer, you can actually tune in with negative latency. It's pretty cool. You can't retroactively point the array, but you can get around that with some tricks.
Sorry, just on the breakthrough lesson, if somebody with a FM, Earth-like radio source, how far out?
Oh, geez. I don't know that sensitivity you're talking about.
And that's what they're trying to do, is that right?
Yeah, I mean, that's essentially it. I think that they're generally agnostic to things like how powerful it is. They just look for peculiar signals, things that don't seem natural, and then they want to follow up on it. And I'm sure that they've done a lot of...
like keep around. The cell phone on the moon is about a James of flux density, and we routinely detect sub-millijamp. So
it doesn't get you very far.
no, that's a cell phone.
They're
actually elastic radar.
Yeah, I think it's trying to speculate like what sort of signals are out there outside of my expertise. But there are definitely people who do. Okay, so to transition into the science portion of the talk, this is going to be kind of just real kind of surface level overview of a lot of different science that we do with the MWA. Not least because I said most of this is actually not my work. The epic of reionization, though, is my wheelhouse. This is what I do, so I'm probably going to be a little bit lopsided. I apologize to my colleagues in the other room for that. Because I hear that you're physicists, may not be familiar with the epic of reionization, so I thought I'd start with kind of just a cosmology picture and what this means. So, if you've been to a cosmology talk, you've probably seen the history of the universe on a non-linear time scale that emphasizes whatever the person is interested in. We're no exception, we always do that. So on the left you have the beginning of the universe with the Big Bang. Shortly after the Big Bang you have recombination. Then we have what we call the Dark Ages. This is the period where there are no stars yet. Any kind of like luminous source is not formed. You pretty much have almost entirely neutral hydrogen gas and CNT protons. But, structure starts to form gravitationally, and eventually you start to form those first stars and galaxies. They're kind of represented by these yellow dots. And they're going to start emitting ionizing radiation, which will then go ionize the neutral gas that's between all the galaxies. This is why I call it the epoch of reionization, because the galaxies are going to reionize the intergalactic medium, the IGM. And they're going to form these kind of bubbles, which are going to grow and eventually overlap. And what we see today are modern galaxies, and the gas between them is almost entirely ion. That the IGM today is almost entirely ion. So we know that happens, because we see this in the cosmic background. So we know that there was a moment of recombination, an era of recombination. But if we look around today, almost everything is ionized. There had to have been this reionization, though it's not terribly well narrowed down when and how it happened. That's pretty much all I'm going to say about that science, and move on to our attempts to measure it. So what we're going to try to measure is the neutral hydrogen that's between all the galaxies. We try to see kind of reionization in the negative, right? So we're not going to look for the sources themselves, we're going to look for the neutral hydrogen. Turns out that signal is about 30 millikelvin, according to theories, and our foregrounds, which are radio galaxies, are about 200 Kelvin. So there's a big dynamic range that we have to overcome there. It's a very non-trivial measurement. We've got the sensitivity. We do the calculation. The MWA has been observing since 2013. I don't think anyone's going to argue with me if I say that we have the amount of data that we need to integrate down the noise and see that. That's not the problem right now. The problem is controlling those foregrounds. They're very, very bright. We have a method for separating them in the data, so they're expected to be very spectrally smooth. Should be able to take a Fourier transform. They will reside primarily in the DC mode, and the hydrogen signal is very bumpy. It has these bubbles in it, so you expect to have a lot of structure, spectral structures. You should be able to separate those. But in order to actually do that, you need very, very precise calibration and very, very precise analysis. And so that is really kind of the name of the game right now in EOR, in radio effective randomization science. So I'll just kind of flash up a couple of plots from our work on this. So this is a power spectrum. You can think about it kind of like a CMB type power spectrum where you have spatial modes, so large things on the left, small things on the right. So it's like the Fourier transform of spatial information. And we have what we typically plot are limits, the upper limits on what the power spectrum of the hydrogen signal actually is. Down here is the kind of a fiducial theoretical value of what we expect it to be at this particular redshift the spatial modes there. So we have a long way to go, right? This is from my analysis in 2016. There are some bins where we're noise dominated. In principle, we could go throw more data at it, integrate it down, but that's going to be a little difficult because our noise level is higher in those modes. It's going to take a lot of data to beat down. So we're betting on these lower modes. We want to access them by overcoming the systematic and getting us down to the sensitivity level so that we can quicker reach that level. So this was from phase 1, my analysis in 2016. I'll show you some preliminary results from Nicole Berry, who has been actually reprocessing the same data set that I used. But improvements in analysis and really good improvements in data quality tests. She actually removed more data and was able to achieve better limits. So her limits are almost an order of magnitude lower than mine because of those improvements in analysis and data quality. And very importantly, she's accessing these lower modes. They're consistent with zero, or at least one mode there is consistent with zero. And starting to open up a few more, which is great. It's indicative that if we keep going, we can find other systematics that we don't understand.
So just to be clear, the reason for the bands of K makes sense it is because of the specific layout of the array.
The missing data right here?
Yeah.
That is something I did not talk about. It's a technical feature of the MWA. When we do our spectral estimation, we do a Fourier transform of our data, and we do that in 2 stages, which introduces a periodic bandpass in our response, and that results in contamination of the mode. So what you typically have there is the foregrounds, which should live, they're crossed out, but on this side of the K-plot, they get, alias isn't quite the right word, but they get reflected into these other modes because of that periodic bandpass that we haven't perfectly corrected.
What's the Y?
The y-axis is millikelvin squared. It's power. It's a power spectrum. So you mean like translated into using like the Hubble constant, things like that? So, oh, I'm sorry. The colors change between these. sorry. In this plot, the black solid was a theoretical, a numerical simulation of what the epic of reionization should look like. In this plot, it may even be a different model. I'm not sure if it's orange one. And this is absolutely model dependent. Like, this can actually change quite a bit depending on whose model of reionization is using, what sort of astrophysical parameters are going into it. And that's actually the excitement of our science, is that a lot of that is unknown, and it's like to manage that.
You mentioned 30 millikelvin of deltas of fluctuation on the 30 millikelvin.
That's right.
Is that right? So you're saying if that's at 3 to 4 millikelvin level, when you square it up, you get about 10 to 15. Is that the idea?
Wait, what did I say? So this, so 30 millikelvin is a fluctuation.
It is a fluctuation. So
That doesn't.
is that right? So 30 millikelvin would be...
The model, I think it's a model dependent statement. I think that 30 millikelvins on the optimistic side for total brightness. Most of these models in power spectrum space are coming in between 10 and 100. So an RMS of 3 to 10. Yeah. So an RMS of 3 to 10 millikelvin. So 30 on the optimistic side.
Yeah.
I know that I mentioned this already, but interest is that reaching the launch level when it starts to that means that this is a little bit
It means that reaching the noise level means that we've kind of done the best we can do with that data, and to get lower, in those particular modes, to get lower, you need more data, which we have. This is not a complete analysis of all the data we've taken so far. But because these systematics are very difficult to overcome, we've kind of taken the approach of taking smaller sets of data, understanding it really well, analyzing that until we get to the point where we are reaching a noise level, and then you can add more and figure out what's the next tallest way to graph.
the noise level obviously means the statistical error.
The thermal noise. We're dominated by thermal noise. Okay, so that was all actually phase 1. Phase 2 has these lovely hexagonal cores, so we're going to try to leverage that. We zoom in on that. As I said earlier, you get many repeated measurements. So, green arrows are showing different baselines, antenna pairs that are measuring the same thing. But the red is showing a different set of baselines. And you can build up a whole bunch of these. Any given antenna is a part of many different unique arrangements. And because many things, you're measuring the same thing many times, you can back out information, like the response of the antenna relative to each other. So it's sort of a counting number of equations or number of unknowns sort of thing. And this leads to something called redundant calibration, which is a method that's out there, so you basically leverage the symmetry in the problem to solve for your calibration solutions, and that gets you a pretty far way along. And actually work that's been led here at Brown with Jonathan's student Wen-Yang Lee has been to explore the trade-offs between these different calibration schemes. And the MWA is uniquely placed as far as I know, the only telescope in the world that has imaging, a pseudo-random layout and a redundant layout together. And so you can do a direct comparison between these different methods. And in fact, use both of them in the same data set. So Wen-Yang actually does like a hybrid calibration, along with a bunch of other improvements that he's done with the analysis too. So he's been able to kind of, this is again very preliminary, but he's been getting lower limits as well. I think his, if I remember right, his is a little bit above Nicole's, but still far below mine. To improve it that way. Okay, so that's pretty much what I was going to say about the EOR, because I wanted to make sure I don't spend all the time on that. because there's a ton of other science that we do at the MWA. One of the themes is galactic and extragalactic science, with the running joke in our collaboration is, that's everything. It's anything that's not caught by the other groups, really. It's a huge grab bag. But, there's a lot of kind of commonality within the group. They use a lot of the same processing techniques and things like that. So it makes sense to put them together into a group that way. So there's kind of a list here, and this is the way that we call it GEG, the Galactic and Extragalactic Group, the way that they have kind of divided themselves into working teams. And I'll try to touch a little bit on pretty much all of these. In fact, I think I might have missed some in my slides, but there's no way I can cover everything in a reasonable amount of time. So everything is very surface level, and I'm just kind of hitting some highlights. There's a lot more out there that you can explore if you're interested. One of the big products of the Phase 1 MWA from the GEG group, the Galactic and Extragalactic group, is this GLEAM survey. So they set out to measure as many radio sources in the southern sky as they could, and they produced a catalog with, I think, a little bit more than 300,000 radio sources, down to, I thought I wrote this down, I think about 5 millijansky level. You can kind of play around. This is kind of cool. It's an interactive tool if you feel like playing around with it. Gleamoscope.infrared.org, or you can just search for Gleamoscope. It works really well on like a tablet. You can pan around and things like that. You can compare with different wavelengths too. And this is then, in its own right, it's a huge effort, and it's also supported a lot of other projects. I'll kind of touch a little bit on that. Another result from the Phase 1, in fact, was using the GLEAM data, was studying H2 regions in the galaxy. So H2 regions, I have this right, show up as absorption in the radio continuum. So you can actually measure things like emissivity towards those directions. And the dots are showing different H2 regions that were identified in our own galaxy. The Phase 2 is going to basically allow deeper surveys. GLEAM was pretty much as deep as the Phase 1 would go, and it covered the whole southern sky. With Phase 2, it can go a lot deeper, such that it's pretty impractical to do the full southern sky at its full depth. Because you need a lot more data to get that low. You actually have to take the data in a different observing mode. You can't integrate as long, and so it's going to be just, even if it's the same amount of time your observation is, it's going to be a lot more data volume. And so practically, I don't think we're ever going to do the full southern sky at the full Phase 2 depth, but what we are doing instead is this GLEAM X, which is like the next generation GLEAM, is going to be deeper by a factor of a few, and it's still going to be up the whole southern sky. And then we're going to have a few other, and again, this is not exhaustive list, but there's the MWA, interestingly deep astrophysical survey, MIDAS, which is going to go as deep as possible on a few select fields, ones that other astronomers are looking at, gamma fields, things like that. And then we have MACE-X, which is a particularly deep one on the Magellanic Clouds. And again, not exhaustive, just a few that we'll kind of highlight. One of the GEG kind of oddballs in a way, because most of GEG is looking at continuum observations. The oddball is spectroscopy, so they're actually looking at the frequency structure, looking for emission and absorption lines. Shanoa Tremblay, who is in the other room, if you're really interested, hike over there and have a chat with her, has basically pioneered this with the MWA. Until recently, has been the only one working on this with the MWA and has had some great results. I'm featuring like one plot here. She's detected a lot of radio recombination lines and several different molecular lines. So these molecular lines, copied down, are potential precursors for amines, and the radio recombination line, you can study thermal mechanisms in the ISM. It's almost like a laundry list, right? I'm just kind of like going through a bunch of things. Another strength of the MWA is that it is very sensitive to diffuse structure. And partially by design, because the EOR was a very large driver for the MWA. And that signal is diffused, and you want to measure many different spatial modes rather than just point sources. But that has the consequence that you can use it for other diffuse structure to try to measure things like the cosmic web. So this is from Tessa Bernstrom's paper in 2017, where she actually used the EOR observation. Just like took those wholesale and used some analysis from EOR collaborators and did a cross correlation with a few infrared galaxy surveys, put some limits on the cosmic web surface brightness, and translate that into a magnetic field strength limit. So it's kind of a cool like mixing between the different science groups. For the same reason, this kind of diffuse structure, you can go after synchrotron radiation that is in things like galaxy clusters, so the halos that you might find in clusters, or you can go after these ridges that may be between clusters. I think there's a recent LOFAR paper that demonstrated this, that they found the synchrotron radiation coming between the two merging galaxy clusters. And so again, that high surface brightness sensitivity is very powerful here, as well as the frequency coverage, so you can nail down the spectral structure across a very wide range. Polarimetry, going after polarized sources. Chris Risley, also in the other room, he reanalyzed the gleam data and found about twice as many polarized sources than we're expecting. So I don't know yet what the punchline is there, but it sounds exciting. He's also able to identify tens of pulsars in that same data set. In phase 2, he should be able to go a lot deeper because of the improved resolution. Again, switching gears, I'm just going to kind of keep going here, so interrupt me if you want to talk more about anything. The time domain astrophysics has been a big part of the MWA from the beginning, and they have a lot of really exciting stuff coming out because of those improvements that we saw early on. So that rapid response is obviously a huge deal, where you can point the array within 16 seconds. You get an order, within 16 seconds you can have the array pointed in a specific direction with a specific frequency choice. That's going to be a very big deal. And then obviously, basically, extended array gives you higher sensitivity to a lot of small things. Interestingly though, certain time domain cases can benefit from a compact array because you can achieve a lot of sensitivity at the cost of larger pixels on the sky. But if you're doing something like a blind search, that's probably fine because you want to search as much of the sky as possible. And you can get away with some computational shortcuts by having a smaller array. So that's actually a key component of the surveillance project. Yeah.
Sorry, I have a question about polarimetry. How does MWA compare with Meerkat or one of the student surveys when it comes to detecting pulsars, especially like millisecond pulsars?
I'm not going to have an answer for you as far as the comparison between Meerkat. If you're really interested in this, I can introduce you to the person that can answer it in the other room.
Say quickly, the higher frequencies are where you want to find pulsars, and it has to be better for finding pulsars. You want to understand pulsar emission mechanisms, so why spectral coverage really helps you get a handle on that. So, for example, the pulse that Meerkat sees and the pulse that MWA sees are different. They're coming from different heights than I do those here, so that gives you a lot of information to try and model pulsar emission mechanisms. But if you just want to find them, it's harder to look at.
let's see. It's probably an unfair thing to do, but I lumped several things into one slide to talk about multi-messenger astrophysics, which is kind of emerging in the MWA community. We've been responsive to gravitational waves from the beginning. We've tried to follow up on any alert that's gone out. Early on, the famous one from August 2017, where there was an EM detection across many different sections of the spectrum. The MWA was the source was not up at the time for the MWA, so we weren't going to see any prompt emission from it, even if we had an efficient trigger at the time, and it wasn't bright enough to see longer duration afterwards. But we're going to keep going for that prompt coherent emission. That's probably our best chance. So there's a lot of tricks we can do, like I said, with negative latency, for example, try to go after that emission from this gravitational wave. And in fact, many of the techniques kind of just fall into neutrinos as well. You get an alert to try to detect a trend in that location. The wide field of view of the MWA, again, is a big strength here. So our field of view is kind of close to the size of the positional eclipses for the LIGO Virgo alerts that go out. And then cosmic rays is another whole category there. This is a prototype cosmic ray detector that's been deployed out on the site, so we can trigger off of that and detect the radio emission from a shower. And this is kind of in beta. We're kind of testing that out. Fast radio bursts, I think, are super interesting right now. If you're not familiar, these are radio bursts that kind of happen. They're very short duration. There have been very few of them detected, although in the last couple of years that number has just exploded with surveys from CHIME and ASCAP, for example. These signals, because they're traveling through an ionized medium, they get dispersed, and so if you look at the arrival time as a function of frequency, you kind of have this very characteristic curve there. You have to try to account for when you're searching. So this is a super bright one, the low numbers, but if you are looking at some of the more recent ones that are discovered, you would not see it in this plot. You have to do the dispersion, so lining it up and collapsing it into a single plot like that. So the really interesting thing for us is that so far there have been no detections of FRBs below 400 megahertz, though there were several detections by CHIME that went right down to 400 megahertz. So there's a lot of indication that we should be able to see something at the top of the MWA band, which is at 300 megahertz. However, we have been shadowing ASCAP, and ASCAP detected, I forget the actual number, I think like a dozen or so FRBs, and we were on sky observing at the same time for 7 of those, and did not detect it. So it put some pretty strong constraints on the spectral shape of the broadband spectrum of the fast radio burst. But with the new with all the upgrades we have, the faster response time, the voltage capture dump is going to allow us to record that data in very high time resolution, which is going to improve that dispersion, and the higher spatial resolution should allow us to get higher sensitivity for this location. Should be able to take. I think this is going to be super exciting in the coming years as we kind of see how this all unfolds. Pulsars have been mainly driven. So I mentioned a couple of pulsars during the polarimetry, but the pulsar study has mainly been driven through this voltage capture system, where we can get the very high time resolution and do the phase folding. So you can study things at high time resolution, do the census of those pulsars, study the emission properties and their particular scattering and things like that. The phase 2 array is where we're going to actually leverage that compact array to do a search for low frequency pulsars, or pulsars in the low frequency. So this is just kind of a map of blue is kind of a catalog of pulsars, and red is kind of simulated what we might be able to see. Okay, so solar, heliospheric, and ionospheric science. I do the UR, and I think that's really hard. Imaging things around the sun and radio just sounds really, really hard to me. So my hats off to you guys who are doing this. The key pieces that you need to do this science, you need to image relatively fast. So we're talking like half-second time scale to capture some of the events and things that they're looking for. And you want to achieve very high gathering range because you're looking at the sun. And so the MWA, again, it has it's instantaneous point spread function. So a lot of radio arrays will have very nice point spread functions, but they rely on integrating for hours. You track a source and integrate for hours, and it actually improves your point spread function. We'll talk more about that. It's really interesting in details, but the point is the MWA actually has a great point spread function instantaneously, and at a single frequency band. So it has really great imaging performance. And phase 2 again, the theme is improved resolution and sensitivity is going to help all these things. So we affectionately call them the SHY group, the solar, heliospheric, and ionospheric group. They have dedicated a ton of resources in the first several years of telescope to really understand their data. It's very similar to the MWA actually. They're really trying to reinvent analysis pipelines so that they can achieve very high dynamic ranges. And actually just this year they released their automated pipeline. It's just going to let them churn through data. So this is another area where you're going to expect to see a lot of progress in the next couple of years in the MWA. These are just kind of a few examples. These are pretty old data, but just kind of demonstrating some type 3 solar bursts that they've detected and studied. A really interesting thing that's come out of that SHY group is a weak non-thermal emission, which I don't know if I fully understand, but they're seeing what look like kind of nano flares. It's a very, very short duration. And I just learned yesterday, Colin Lonsdale, who's the head of that group, to give an update, that they actually discovered that they're very periodic. These kind of like bursts in flux level that is demonstrated by so what you're seeing here is a bunch of different bursts that are just kind of, they look like kind of scattered noisy stuff. It's like popcorn almost. What he did was he showed if you do the imaging and look at a single pixel and then look at a dynamic spectrum, so frequency and time, and it's a lot more clean. It's just a regular pulse. That's really neat. So they're I don't think they're the first to like this weak non-thermal emission, but they are about an order of magnitude in terms of the faintest non-thermal detection emission. They have detected about an order of magnitude lower than anybody else. And again, everything basically is just going to get better. That improved resolution is going to let them narrow in on the specific pixels, which will improve their measurement of those flares or nanoflares. Interplanetary scintillation. So, if you're not familiar with this, so the sun here, and there's some kind of solar wind, just ionized medium kind of sailing off of it. And if you're looking at some source over here, you have a nice coherent wavefront come in that gets corrupted by that solar wind. And what you end up seeing is the flux of that source is going to be it's going to twinkle, actually. It's kind of a baseline, and then what you see from scintillating source. So you can use this to map out space weather. Actually, the pulsar group is using the same technique to study space weather so they understand how that's going to affect pulsar timing arrays for doing gravitational wave studies. One of the probably most exciting results that came out of phase 1 actually is of the Ionospheric Ducts, which were detected in 2015 by Cleo Leroy. So you can use that kind of same idea of light turbulences, ionized medium. It will corrupt the wavefront, and if it's going through an ionized medium that has a gradient, like the ionosphere might have, it'll actually shift the position of sources in your images. And so she mapped out the relative positions of sources, the positions of sources relative to their catalog positions, and saw there's kind of these systematic shifts. And they form these, the lines are there to guide your eye, but even if you have the lines there, it's really pretty clear that you have kind of these corroborated, kind of like wavy shape to it. And this was a first detection of these cylindrical density structures that are in the plasma sphere, and they're aligned with Earth's magnetic field. So that's what these lines are for Earth's magnetic field in that image. So that's really cool. Okay. So this is actually pretty good timing. Kind of wrapping up here, that was again a very brief overview of those 4 main science themes. We also recognize that not everything fits into those 4 categories, so there could be all kinds of other things we can go after. There's been a lot of work on space situational awareness, so this is trying to detect satellites and space debris through reflections of RFI. Radio frequency interference, for example. You also could do, kind of related to that, is trying to detect meteors that may be entering the atmosphere. And then SETI we've already kind of talked a little bit about. Just kind of the last thing I was going to mention is we have a very large archive. It's, I think it's pretty significantly more than 30 petabytes right now. We have this ASBO, All-Sky Virtual Observatory website. Anything that's older than 18 months is public. Anyone can go on there and download data and play around with it. There's an example of Stephen Kingday, who he might be in the other room, but he's probably gone. He used that archive. We saw that was an interstellar asteroid that came by about a year ago, a little bit more than a year ago. He just dug into the archive and thought we had some observations where we actually looking right at it and did a little SETI search on it to see if there were any kind of anomalous signals coming off of it. He didn't find it.
Sorry, but what signal was coming off it that he observed?
Nothing. I don't think he saw anything.
Oh, I see. Sorry, he looked.
He looked.
Yeah.
He kind of did spectra and things like that in the direction of that asteroid. That's right. Not report anything, and it's public data, so I'm just saying. Actually, I don't know if that is public data. I don't know when that asteroid came by. It'll be public data eventually, not already. Okay, so my summary slide is kind of silly, but the MWA has been operating since 2013. We have a lot of data in the can. We're continuing to analyze both old data, and we're diving into the new stuff that has absolutely taken since the phase 2 expansion. There's been a ton of progress on all the science directions on things. So, there's the URL for our telescope's webpage, and I'll be around today to answer your questions or ask me right now. Thank you.
Time for questions, Brad?
Sorry, I'm terrible at like remembering to actually point these things. Hang on, I have to like write things down because I will screw them up if I don't. So a radio telescope, the angular resolution is dependent on the frequency. It scales linearly. But at 154 megahertz, the angular resolution is 1.3 arc seconds. Okay, so this actually goes into that, the idea that a lot of other radio telescopes will talk about their awesome imaging fidelity when they integrate for a long time, because they're actually using the fact that the Earth is rotating to sample other Fourier nodes. So they're using, like, those baseline antenna separations are actually moving, and you're going to take advantage of that. So with the MWA, it's also true that if you let the Earth rotate, you're actually going to improve your point spread function. It's going to get better. But there's a trade-off, because you have to kind of point towards whatever you're looking at. And the way our beamformers work, there's little boxes here. We can't physically point the array, and so we do it electronically. And it's done with physical delays of signals. So essentially what I'm trying to get at is the direction that you're pointing is quantized. There are kind of fixed positions that you can point to. So you can do long integration and you very much improve your point spread function, but it's not quite as clean as some of the like the dishes that will almost continuously point, that will track very smoothly. MWA does not track like that. Does that answer your question?
Yeah. I really want to affect the angular.
Yeah. So that definitely would affect the angular resolution. If you are looking at something at the horizon, for example, your point spread function will actually be very oblong. Go that way. You'll be much larger in the kind of elevation direction and less in the direction. But yeah, you're absolutely right. It's a position dependent.
For people who are outside the field a little bit, occasionally something surfaces up for any excitement high enough that you can notice that there was something with the 21 centimeter observation in the early cosmology era, looking and the signal was anomalous, and there was a suggestion that it was related to Dr. Scatter and so forth. Yeah. Phase 2 had anything to say about that?
Okay, so let's go unpack there. So the detection you're talking about came from an experiment called EDGES, which is what we call a global experiment. So rather than looking for fluctuations in the power spectrum, they're looking for the total brightness. And what they saw was there's a dip in the brightness of the hydrogen signal as those stars are starting to form. That dip is about twice as deep as any theory predicted. So the PI for that project is actually a guy I work with that is on stage, Doug Bowman. And I was a little bit privy to what was going on ahead of time and saw him kind of shop around with all the theorists. It's kind of really interesting to actually see this because he asked lots of theorists, is there any way that this dip could be deeper than, I think, 250 millikelvin was they're saying, no way could that happen. And he published and said, actually 500 millikelvin, and then suddenly it just exploded in the papers explaining it. It was pretty interesting. But, so, depending on your interpretation of what causes that signal, and the general kind of ideas are either you messed up, let's rule that out for now. You can have dark matter scattering or anything that's going to cool the matter faster than expected. Or you could have a surplus of radio background emission that might come from super high redshift quasars that nobody actually knows how to form. That doesn't make a lot of sense, but if you had an excess radio background, that would create that signal. And then, so you have to kind of latch onto a theory there and then propagate it through the power spectrum into the epic of randomization. So there are predictions out there that there's a huge boost in the power spectrum that would get us a lot closer, a lot faster. So we're optimistic that that's right, but we have not. Phase 2 does not have anything to say about it yet, because we don't have a detection, and we haven't ruled anything out yet.
But I may be right here. Phase 2 can do some major
It has the sensitivity. Like I said, we have the sensitivity that we can get to those levels, but the real name of the game right now is the foreground.
Let me add one thing. So the edges detection was centered at 78 megahertz. Phase 2 goes from 80 to 300 megahertz.